Good afternoon and welcome back to our next session for PyCon 2025. Hope you have all enjoyed your lunch and are ready and eager to hear from our next speaker, Mr. Anthony Shaw, presenting My AI is Slow, Make It Faster. Thank you, Anthony.
All right. Cool. Hey, everybody. I hope you enjoyed lunch and have been enjoying PyCon AU so far. So my name is Anthony, and I'm going to be talking about AI performance. And when I say performance, I mean like speed performance, not how good or bad it is at doing things. So before we get started, a little bit about me. My name is Anthony. I work at Microsoft. I'm a Python Software Foundation Fellow, and I'm also a fellow at Macquarie Uni. And people talk about a scale of AI from I've drunk all the Kool-Aid, and I think this is going to be the greatest thing that's ever happened, to I think it's the worst thing that's ever been created. I'm sort of floating somewhere in the middle, and to be honest, I kind of waver day by day between this is a terrible idea and this is amazing and it's changing everything. AI is quite unpredictable. It's very, very difficult to work with. For someone who's come from an engineering background and you expect things to work the same way each time. And the way it surprises you day by day is unbelievably frustrating. And then sometimes you get these moments of joy in there as well, where it's just saved you a lot of time. So you can follow me on socials. I'm on lots of different platforms. Also, I've written a book called CPython Internals. And it is all about the internals of CPython and how it works. So if you're interested in that. I also made this thing called VS Code Pets, which is an extension for VS Code, where pets walk around. It turns out to be really popular, and frustratingly, it's the most successful piece of software that I've ever written. Just coming up to 2 million users now. Just yesterday, someone on the Windows team messaged me. I work at Microsoft, and they were like, "How can we get this into Windows?" And I was like, the productivity of millions of people around the world is going to decrease. It's going to look really good on my performance review, so it's a sacrifice that I'm willing to take. But anyway. So our agenda today is that AI is slow. If you've used it, you will have realized that. We're going to look at some requirements in terms of like performance and what your expectations are. I'm going to spend a big chunk of this talking about benchmarking and performance tools and things like that and how we can use them with AI. I've got a few tips to improve the speed of how you're calling AIs. And there's some takeaways. So there'll be a nice slide at the end that you can just take a picture of. There's all the bits you need to know. My promises to you today as well, nothing in this talk is proprietary. I do work for Microsoft, but everything here is open source. Everything is free and available to download and use yourself. Nothing has any weird licenses. And this is all based on experience as well. So these are things that I've been doing as part of my day-to-day work. And I just wanted to share some of these lessons with you today. So this is actually an example I wanted to use. So this is me on a train from Bordeaux to Paris. This train goes 300 kilometers an hour. And I had 2.5 hours. So a nice casual time to look out the window and really not very much to do. And we had Wi-Fi on the train as well, which is always dangerous because instead of relaxing, you're like, oh, I can do things on the internet. That's more fun. So I wanted to actually just make a game and then just play the game on the train. And the game that I worked on was this, which is a Sudoku game, but instead of using 1 to 9, it's hexadecimal. So on the train from Bordeaux to Paris, I basically worked on this with the AI doing most of the heavy work because, well, firstly, I was on holiday, so I shouldn't have been doing any work anyway. I just wanted to do something fun. There was no obligation, and it took ages. So like 2.5 hours to make a game is impressive, but every time I'd ask the AI a question, it would go away for a couple of minutes, come back, and give me an answer. But I could look out the window and just, watch France go past, which is lovely. But that's not always the case. And in terms of user expectations, I've been working on web benchmarking for many, many years, and also performance of applications and code running on computers. And if I said to you, is your phone like fast or slow? It's a subjective question. But you know that when you use a system, like when you use the menu on the TV, for example, if you've got one of those smart TVs, it kind of feels laggy, it feels a bit slow. And this is because you're, over time, using technology, your expectations are that if you're using something on a local system, like a computer, like a local computer, your expectations are within about 10 milliseconds to 100 milliseconds to when you click on something, touch something, that it responds. And if it starts to take longer than 100 milliseconds, it feels slow and it feels laggy. So if you've ever upgraded from one phone to the next model and it feels snappier, the differences can be like 10 milliseconds. If you're working on the internet, though, if you're loading a website, if you're doing a search online, your expectations are shifted slightly further to the right. So you would expect, like a web search, a typical web search, is about 50 to 100 milliseconds. That's how long it takes. That's actually got slower over time, not faster, because they've put more and more crap into the page results. But your expectations when you're clicking on and loading websites are roughly between 50 milliseconds to a second. And lots of data shows us that if a page takes a second to load, users do get bored, and then they find other things to do. So your expectations kind of shift. When it comes to AI, it's even further to the right. So, when you've been learning as you've used like ChatGPT or something else, that if you type in a question, it will take a few seconds to respond. And there's really kind of this shift with what you deem as snappy and what you deem as fast. And the point I want to make early on is that if you try and stick AI into things that are further down the left of this scale, like local time and internet time, you've basically introduced this lag to users, and all of a sudden things feel slow. There's also another trajectory to this, which is Australian internet time, which also seems to be getting slower over time somehow. So when is slow bad? So in this example, you've got a search box, and I have seen this in products where they've got a basic search functionality, and it used to work on a database, and it would take out keywords and do a keyword search on a database. So users know when they type into that box, it's going to look for keywords. And over the last 20 years of having web search, people have intuitively know that when there's a search box, you don't write written sentences, you don't write fully formed sentences, you just write keywords, and then you click search, and it gives you back answers. Now, what has been very tempting for people to do, where you've got an expectation that that's going to respond pretty quickly, what's been tempting for people to do over the last few years is to add AI to the search. So where users would previously type in a question or a series of keywords, they would then introduce AI so that AI could give you more customized or smarter answers or whatever it is. The problem is that you've basically shifted the user's expectation that it will respond in 100 milliseconds, 500 milliseconds, to it taking several seconds, and also it going from a keyword search to a sort of vague AI kind of search, whatever that is. So this is where I found that people have been really, really frustrated because it feels slow to interact with these systems. That, as an example, there are 2 apps on my phone that have done this recently, made by some very large tech companies, where previously I would search for a post on socials or something like that, and then AI would kind of try and do extra things that I wasn't looking for, because really all I wanted to do was a keyword search. I didn't want a smart AI search. So sometimes slow is actually okay. And I use this other example where I have a question. It's not a search. I have a research question. And I can click go, and it can come back and say, OK, I'm going to research your question for you using AI. I'm going to look online. I'm going to read some papers. And it's going to take a couple of hours. And so my expectations are set. It's pretty clear what's going to happen. And also what I'm looking for is involves a lot more information and a lot more searching. So I'm quite happy for the AI to take its time. But there are two different expectations. And so the first point I want to make in the AI thing is that users have an expectation to how things respond when they run locally, when they run on the web, and increasingly they have an expectation to what happens when you interact with AIs. So to summarize my kind of usability points, don't put AI in the way of something which is otherwise fast and efficient, especially if it doesn't really add much value. Search is my main one that I keep bringing up, because AI almost never improves search functionality. Like, search is a solved problem. It's very efficient. It scales really well. We have plenty of algorithms to do search. AI can do like customization of the answer from the search, but like, don't put AI in the search. Don't wait for the entire result. So I'll come back to this in a second, but basically we stream results back from AI so that the user sees the kind of way it looks in ChatGPT and other chatbots. It kind of feels like the AI is typing back to you. But actually what's happening is, as it's computing the answers, it's sending back the stream back to you. And I'll come to some details on that in a minute. And don't use reasoning models, and I'll cover what they are a bit later, unless you actually need reasoning, because reasoning models are all very, very slow today, and a lot of the time you don't actually need them. So using AI to enrich features is great. Having the option to disable and dismiss AI features is also really important, because there are a lot of concerns about AI safety and privacy at the moment, and also whether usability actually gets worse because you've introduced AI. Giving users the ability to switch that off, I think, is critical. And stream back the results. I mentioned, so this QR code at the top. I've included a few QR codes in this talk. Only one of them is a Rickroll, but this one is to some guidelines that we've published. And they're basically, if you're designing a system using AI, there are a set of guidelines that we have called the HACS guidelines. It's basically a UX guidelines for AI-enriched applications. I can't remember what it stands for, but some very smart people at Microsoft have sat down and said, in an ideal world, here are the 16 things that you should do if you've got AI in your application. And yes, not all of those things are done in Microsoft products as well. They are guidelines. They're ambitious. And I really wish that more product managers would try and keep to some of them, especially. But there's some really smart ideas in there, including actually the keynote this morning about the sort of AI ethics, challenges with biases and stuff like that. There's a lot of guidelines in there. There's also a lot of lessons that we've learned over the years from putting bots online, which have caused all sorts of challenges. So there's a tool called Pyrit, Pyrit. It is basically a red teaming tool for AIs that gets it to try and produce all sorts of horrible things. And then it gives you a checklist to see whether you've actually put safety guards in place. So yeah, we have learned some lessons. So when it comes to actually measuring performance, if anyone out here has done any web benchmarking, like web app benchmarking and stuff like that? Okay, a little bit. So normally what you do with web benchmarking is you would send thousands of requests to your application, and you'd measure how long it takes to get back the answer. And it's normally just the full response, and then you'd also measure how long it takes for the browser to render the page and load up all the assets and stuff like that. So that's kind of how we measure web applications. AI is a bit different because the way they work is they actually produce streams of tokens. So in the question, what is the capital of France, which has become the go-to test question for AIs. I don't know why. It just is. So if you ask AI, what is the capital of France, it will send you back these tokens, and each token basically represents a whole word or a part of a word. Over the network, it actually sends those tokens back in separate packets, in separate HTTP response parts called a stream. So you send it one request, and you don't get back one response, you actually get back several responses. So with pretty much every AI these days, you send a request, and you get back a stream of data, and as you receive the stream, you draw it on the screen, you save it to disk, whatever it is, And this basically means that you can give the user the feedback really early on that they're getting information back, and they can start to read the answer. So the time, in terms of how we measure this, the time between the moment you click go and send the request to when you get back the first token is called the time to first token. Tokens come in chunks, so I also call it the time to first chunk. That's a really important metric, because it basically says how long did it take for the model to think about the answer before it started sending you back any information. Then you've got the total time, which is how long does it take for it to finish its answer. It's also important to note that sometimes I'm pretty sure we all have done this, we've cancelled an AI, stopped it, because it's just been waffling on for ages, and you're like, I don't care, you got to the point ages ago. At least the good thing is you can kind of stop the stream earlier on. There are some other metrics as well which are important, like the number of characters. So the capital of France is Paris, it's 31 characters. There were 7 tokens, 3 chunks, and so I can basically work out what was the total time, how many chunks were there, and therefore what was the throughput by dividing the two. So like what is the chunks per second, or what is the tokens per second for that AI model. These things are important because it basically shows you how fast AI can write back to you. And there are huge differences between different AI models, which is what I want to spend some of this time looking into. So on the right-hand side is a graph, which it was produced by a tool that I made, and I'll give you a demo of that and how it works. Basically, it will produce these 4 measures. One is total time. These are all box and whisker charts. If you're not familiar with box and whiskers, basically the box, so the colored box, is the interquartile range, which is basically like the middle range of values. How long did it take for it to answer? And what is like the most common part of that? And the black line in the middle of it is the median. And then any little circles and stuff like that are outliers. And the whisker is basically showing like what are the outside quartiles. So box and whisker charts are really helpful because you're looking for how thin is the box. So like how consistently does it give you the same response or the same time. So the bigger the box, the more variable it is. How big is the whiskers? So like how spread out is the answer? And then these little circles are basically where you've got these anomalies in your data. So box and whisker graphs are great when you're running performance benchmarks because you're looking for a nice small box with small whiskers and you're looking for it to be consistent. So basically on this one, I ran a benchmark against 4 different models, asked them all exactly the same question. And in terms of like total time, model C, which is Llama 3.2, responded within like a couple of seconds, whereas 5.4 went all the way up to a minute. So it's a pretty big difference to answer exactly the same question. What's important here is that we've got the total time, which I kind of covered in the last slide, the time to first chunk, so that's like how long it took to think about the answer, the length of response, which you'll notice there is an enormous difference between the models and the length of response, and I'll talk about that in a bit, and the chunks per second. So what you can do with this tool is effectively you can give it any range of models to test against, and you can get this graph. And so if you've got a problem or a question and you want to figure out which is the best model for us to pick, it gives you a nice comparison. So let me show you that working. So the way this tool works is it's built into a command line interface called LLM. Has anybody used the LLM CLI? Okay, a couple of you. So I really like the LLM CLI. It's a tool by Simon Willison. Basically, you can do all sorts of cool stuff. It's a command line interface for you to run locally, so you can do things like pipe stuff from your local disk directly into an LLM. So if you've got like files and things and you want to extract data. It's also very extensible. So in terms of the models that you're using, you can install plugins to talk to basically anything. So you can run models locally, like I'm running lots of models on my laptop. You can connect it to OpenAI.com, AWS Bedrock, Azure, GitHub Models, basically like any model hosting platform or one that you're running locally on your machine, or if you've got a server and a GPU cluster, you can connect it to that. So with LLM, once you've got these plugins, you can run LLM models, and it will list what models you have available to you. I have a lot, because I do this as a job. So I've got a lot available to me, and I can basically kind of pick and choose which of these models I want to compare and see like where they're hosted. So for example, I was doing a comparison between GPT-5 in Australia and one hosted in the US to see what the difference was with performance and what difference it made. If you're running local models as well, so whether that's using something like Ollama, for example, so in Ollama, you can download and run a number of smaller language models and also embedding models, and you can benchmark those and test them as well. You need a pretty decent laptop to do that, so I will caution you. Also, don't do it with the laptop on your lap. It gets uncomfortably warm. So the benchmarking tool is basically a plugin for LLM called LLM Profile, and it gives you this extra command where you say LLM benchmark, and then your prompt input, and then you list as many models as you feel like. So they can be models online, they can be models locally, they can be models on different clouds, different locations, whatever. And then you say how many times you want it to repeat the test, and then if you want it to produce one of those graphs, and then you just ask it for a graph. And it will give you back this sort of summary table of information. So it will run that test locally. If that is too simple for you, if you want to do some more complicated test scenarios, for example, you want to try to see what the difference is if the temperature is lower in one test but higher in another, or you want to test like one model in one country and one in another, or even test two different prompts, then you can do that by providing this YAML file with like different inputs and different questions. So like the go-to question of what is the capital of France, we can compare that with what is the capital of Azerbaijan, and the differences in length, for example, and the differences in thinking time are actually quite different between the models, between those questions, even though the questions semantically are the same. Like, what is the capital city of this country should be a simple, straightforward sentence answer. However, in some cases, it will write you multiple paragraphs of travel tips about Azerbaijan, including the answer. Does anyone know the answer? No Formula One fans in the room? Baku, thank you. That is next weekend. OK. All right, so once you've done this and you've got your graph, you can see the differences in performance between the models. So let's get on to how do we actually make it faster? My number one tip is to look for shorter answers. There was a talk yesterday, actually, Jack's talk. He talked about how Charles Darwin was paid by the word, which is why the opening part of Tale of Two Cities is so ridiculously long. These LLM models are rewarded in their training for their ability to solve problems, answer questions, and solve coding challenges. There is no penalty for the length of the answer for them to achieve that. Therefore, they are also paid by the word. The way that you pay them is also by the token. So LLMs will give you really, really long answers when you don't ask for it. So what is the capital of Azerbaijan? The capital is Baku. Everyone knows that. This one here gave me, instead of taking 1 second, it took 100 seconds, and it wrote 4 paragraphs about Baku and its cultural history. And it also did not mention the Formula One, which is ridiculous. Like, why would you not? The total time and also the time to first chunk was significantly higher for that as well. So my first kind of suggestion is that you should get shorter responses. You can do that either by using a smaller model, or you can say in your prompt, I want a single sentence, or I want 2 to 3 sentences, or I want 3 answers. You basically set the expectation to the model as to the length of the prompt. If you don't do that, if it's completely unbound, they will tend to, especially the bigger models, they will tend to produce way more output than you actually need, and it will take a lot longer. It'll also cost you more money. Oops. The second thing is distillation. So this is basically, we don't have time to cover it, but what they've done is they've condensed models down so that you've taken all the weights, so the number of parameters of the model, and you've reduced them by basically, it's called Matryoshka, so those dolls you get where one inside another. And the reason they've used that analogy is because you've basically taken the answer from a big model and you've stuffed it into a smaller one. So instead of it having to know about every single capital city and how to think about it and stuff like that, it's kind of cheated. It's got like a lookup table and it's saved the information. So like that's a very brief summary. Distillation means that you can run a model with the same kind of corpus as a much bigger model on smaller hardware, and it's also a lot faster. So when you see in Ollama, you've got these small models, like 7 billion, 8 billion models. It's basically the full model, but they've asked it lots and lots of questions, and they've condensed it down into a smaller one. You can see this in this benchmark. This is the Qwen 3 series model with, and basically I've taken a larger one, which is 8 billion parameters, and I've taken the smallest one, which is 0.6, and you'll see that the time it takes to give me the same answer, answer the same question, sorry, which is, can you come up with some names for my pet octopus? It takes a lot longer for an 8 billion parameter model than it does for a 600 million one. Also, the length of response goes up. And then, weirdly enough, it comes back down again. Between 4 and the 8 billion version model, I don't know why, but it gives you shorter answers for 8 than it does for 4, which is why you should test things. Because you have assumptions and you have generalizations, but when you use tools like this, you can actually come to different conclusions. The next point is quantization, which is a really cool word to say. And it's something you can just drop into conversations all the time. And basically, the theory is fairly simple. If you have a range of values on a scale, you can basically get the smallest one and the biggest one and say, OK, the smallest one is now the smallest point in a different scale. So if we did scalar, that's int 8, which is 255 different values. So basically, the smallest one is now minus 128, and the biggest one is now plus. And basically, what we're doing is taking data from a 32-bit or 64-bit value into a much smaller format. The reason you do that is because CPUs and GPUs can do that calculation much, much faster. So like 4, 8 times faster. So basically, what we're doing is we're approximating the data inside the model, like the weights basically inside the model, into different values. Do you need to know any of this? No, not really. All you need to know is that by using this technique, you can run things on smaller hardware, and it will run faster. So when you hear quantization, or you see there's different flavors of a model that you can pull, you can use a smaller model to basically run similar answers and get similar accuracy, but with much smaller hardware. The other thing you can do is something called semantic caching. This is a really, really new technique. In Python, there is a great function built in called LRU cache. You can use it as a decorator on a Python function. It basically means if you call the function the same with the same arguments, it will cache and give you back the result the first time. You should use LRU cache a lot where you have a function that takes a long time to execute, and you just want to cache the responses into memory. So I really recommend using LRU cache. The problem is that it is very specific. So if we ask the same question more or less, it's just going to compare the strings and see them as the same thing. So in the QR code in the bottom right-hand corner, that one is not a Rickroll, is a link to a repo that I put together for this talk with a demo of something called a semantic cache. It is a function decorator. And instead of using like literal comparisons, it does an embedding model similarity. And you can tell it what trigger point you want to cache the inputs. So basically, if you had the question that I had in the last slide, which is what is the capital of France and what is the capital city of France, it would see those as being very similar questions and actually cache the answer. This is quite a new technique. and we're still kind of working out some details on this. But it really gives you the ability to improve performance where you've got users asking very, very similar questions. Okay, the next technique is something called model routing. This is where you have an input, and you're basically trying to direct it to the cheapest and fastest model. There are lots of challenges with this approach, as it has been unveiled with the GPT-5, which has got this built in, and I don't think people realized they were using it, and that's why there's been this mismatch in expectations with GPT-5. But basically, you get a user question, and you say, is this a simple question? If so, give it to a cheap model. If it's not, then give it to a chat model, and then otherwise give it to a reasoning model. We have effectively run out of time, so I'm going to summarize the talk. One, smaller models are faster. The bigger the model, the longer the response. Models are paid by the word, so keep that in mind when you're using them. Longer responses take more time, and users have preset expectations on responsiveness as well. So yeah, thank you very much for your time. My name's Anthony, and I'll give the last slide. Here we go. All right, thanks very much.